Saxon Advanced Mathematics, lesson 30. It's a two-parter, although most of it is going to be this adding vectors. This is trig. We also have a little bit of geometry at the end. But let's talk about adding vectors. We did this a lot last year, so it's mostly review. But adding vectors is saying, okay, here's a point that we have, and we're going to affect it with force 1, which has a strength, which we call a magnitude, and a direction, right? And then we're going to go from there, we're going to hit it again with a different force, with a different magnitude and a different direction. And then we're going to figure out where is this ending place, right? Now, the way that we do this involves several steps, because what often happens is we're given the original forces, the original vectors, as polar coordinates. That's often how this starts. Polar coordinates have a force and a direction. It looks like this, right? We often call this is the direction or the angle, and this is the strength or the magnitude, but I prefer to call it the distance. Now, these are really great for describing these forces, but when we go to add them, we can't do it with a polar coordinate. So what we do then is we change them into rectangular coordinates. And remember, rectangular coordinates look like this. They have a distance, they have a sign and a number to the right, and a sign and a number to the up, if you will, where, you know, right is the x-axis and u is the y-axis. Now, once we switch them into rectangulars, we can actually add rectangular coordinates. Right? And that's easy. We just stack them on top of each other and literally just add them, right? The numbers add and subtract. That's really straightforward. And then sometimes we have to revert back to polar coordinates. And so this is the kind of the steps. We go from polar to rectangular, then we add the rectangular, and then sometimes John wants us to revert back. So these problems involve a lot of horsing around, but they accomplish a very useful thing. They allow us to go directly to that new point, right? So they're useful in real life, in physics, in engineering. And so that's why we practice them, but they're just a lot of steps. So let's remember how to do these. You do need a calculator with trig functions on it in order to do these. I will give you the answers if you have any, and I'll remind you of how to work the buttons. If you have any problems with your calculating, let me know. Also, when we're doing these problems, please resist the temptation to do any other calculations with your calculator. Just use it to find the trig values that you have to use, but don't use it to do like the addition and subtraction. You don't need that. Find the resultant, okay? Resultant means the sum of 4 at 20 degrees and 7 at minus 230 degrees. Okay, so the first thing we're going to do is convert to rectangular. And the way that we do that is by drawing the triangles. Okay, 20 degrees is going to be in the first quadrant. I like to figure out which quadrant it's in and only draw that quadrant so that I can get to the part of the picture that I need to without drawing a great big thing or squishing it all. Okay, so I like to find the quadrant. This is 20 degrees. This is the hypotenuse, so I know that's 4. Okay, now I know that I can use cosine to find this one and sine to find that one. No, I said that wrong. Cosine to find this one, sine to find this one. All I know is I want cosine first. So I'll have to do 4 times the cosine of 20 degrees, and that will give me the right value. Yeah, so that will give me this one. And then I'll use sine to find the up value. I don't know what I said, but that's what I meant. All right? Remember that the way to enter these into your calculator is to do 20, and then cosine, you'll get a value, and then times 4. This value should be 3.76, and this value should be 1.37. Remember to round properly, right? Don't just truncate, don't just chop off the other decimals, but round it the way you know how to round. Okay, now I'm gonna do the same thing over here. Minus 230, let's see, I'm thinking backwards then, right? Because it's gonna be going down from the x-axis. So that would be 90, 180, and then I'll need another 50 in the second quadrant, right? 90, 180, and then another 50 will get me to minus 230. My hypotenuse is 7. Okay, so here I go. My right value is the one I use for cosine, so 7 times the cosine of 50 degrees. And my up value will be 7 times the sine of 50 degrees. Okay, just remember to always do cosine first, and that will give you the sides in the right order. What we're doing is we're calculating this side and this side, and that side and that side. These values, this equals minus 4.50, and this one equals 5.36. Okay, so now I have translated these from polar coordinates to rectangular coordinates. Now I can actually add them. So what I like to do is draw myself a chart so that I put everything in the right place. And then I'll add them, and then these are the blanks I need. Okay, so I've got positive. Grace is having crazy puppy dreams and she's wagging her tail. The up goes over here, and it's plus 1.37. Now this point will go down here. First the right, minus 4.50, and this one is plus 5.36. Okay, so now we'll take the difference between these, which is minus 0.74, and then we'll add those because they're both pluses, and that is 6.73. Okay, so that is the coordinate of our point, right? We started with a point, and first we bumped it this way, and then we bumped it that way, right? Because we took it in a completely different direction. So this point represents the ending point of our, imagine, for some reason, this is weird. I imagine putting a peanut in its shell on a sidewalk and having a squirrel come along and bump Why? I don't know why my brain thinks these things, you guys. I'm sorry. But I imagine the squirrel bumping that peanut along the sidewalk first at 20 degrees for a distance of 4 inches. And then he comes around to the other side, right? And he bumps it at minus 230 degrees for 7 inches. Where does it end up? Well, this point tells us where it ends up, but let's draw a picture of that so we can get a better understanding. Let me make sure I got the right answers. Okay, so I'm going to copy this to the next page and we're going to draw that triangle. it is minus 0.74 to the right plus 6.73 up. Okay, so this triangle means, let's see, it's to the negative on the x-axis and the positive. So it's going to be in the second quadrant. And I'm going to exaggerate this a little bit. This is going to be 0.74, this distance. And then it's going to be like this, right? And there's my right angle. And so this is 0.74 down here. And then this side is 6.73. That's my up, right? And there's where my peanut ended up. And the squirrel just gives up and runs away. Or maybe he sits here and cracks it open and eats it. I don't know. And what we're trying to do is we're trying to get our answer back into polar form. And it helps me again to draw a box to show the shape I want my answer in. This is going to be the angle. And this is going to be the hypotenuse. The angle from 0 degrees, right? We can't just measure this angle. We need to know this angle. Okay, that'll be interesting. Now, to find the hypotenuse, we could use, well, no, I'm not even going to say that. Let's use Pythagorean. A squared plus B squared equals C squared, or C equals the square root. Okay, so this is our easiest tool to calculate the hypotenuse that belongs here. And we will always have these two legs because those are the rectangular coordinates. So to find the hypotenuse, I like to say H, because that's what this side is, right? That's the hypotenuse, and that's what we want there. It's going to be the square root of each of these legs squared. 6.73 squared plus 0.74 squared. Okay, you can definitely use your calculator for this. All right? Take this number, square it, add it. Now you'll have to use parentheses for this one. Start the parentheses, enter this, hit the x squared, close it, equals, and then square root. If you need help, rewind this video to where I started saying that and go through it again. I'll say it one more time, all right? Pause me and grab your calculator and go through this if this confuses you at all. Ready? Okay. Enter 6.73. Hit the button that says x squared. That will square it. Plus, now you need the parenthesis marker, 0.74 squared, close parenthesis, equals. That will then do the adding for you. Once you do the equals, you'll get like 36 plus a little less than 1, right? So that'll be like 37 or so. Yeah, it'll be more than that because of those decimals, but it'll be more than 36. Then you take the square root and you'll get a hypotenuse equal to 6.77. Okay, this goes up in the box. It's part of our answer, yay. We are rounding at this point to 2 decimal numbers. Okay, now we're ready to find this angle. And what we will do is we will use inverse tangent to find this. Okay, so this is the tool that we use. You can do these in either order. I kind of like to do this one first and this one second, just because that's how we fill in the blanks. That's got a decimal in it. Okay, so how do we do this? Well, we remember that tangent equals over Arthur, right? And from this angle, we know what our, I'm going to take that away. The tangent of this angle, which we don't know, is equal to opposite 6.73 over Arthur 0.74. Okay? So you can use your calculator for this part too. You take 6.73, you divide it by 0.74, then we're going to use the inverse tangent button, which to get that, you'll have to hit the second button on your original keypad, and then the buttons will change and you'll get this function. And that will give you the angle for this. Okay, so first, find this as a decimal. Then 2, hit second. Then 3, hit tangent of -1. Again, that's the inverse function, and what that will do is it will tell you the size of the angle. You'll get theta equals 83.73 degrees. That is not the number we put here. That is the number that is here. Let me just draw this a little bit over again. This is our picture down here. This is the same thing. This angle is 83.73. That's cool. That's good to know, but we want this angle, right? So how do we find that? We take 180 degrees, which is the whole shooting match, and we subtract the 83.73. That's the part we don't want. And when we subtract that, we get 96.27. That I expect you to do in your own little head. Don't use the calculator. And this is the number that goes up here. And that's our final answer, right? So that tells us that if you want to find the place where the squirrel pushed the peanut in those two vectors that we had before, you go to 96.27 degrees, and then you go up 6.77 units, whatever we're measuring in. And this is our final answer. That was a lot of work, wasn't it? I mean, I wrote really big and I skipped a little bit, but that literally took me 2 pages. Make sure you get these notes down, though, about the tools that you use to solve. We use cosine and sine, right? The way I set these up, where it's the hypotenuse times cosine of the angle and hypotenuse times sine of the angle, that will always be the same. This is the automatic thing you need to do here. Then we add them, and then we use these 2 tools to go back. Notice that when we're going from vectors to rectangulars, we know the hypotenuse and the angle, and we're trying to find the 2 sides, right? Then we find the combined 2 sides. Then we do the same thing in reverse. We know the 2 sides, but we want the hypotenuse and the angle. So there's 4 pieces of information on these triangles. Each of the 3 sides plus the angle. No, there's 4 pieces. 3 sides plus 1 angle. And for polar, we need 2 of them. And for rectangular, we need the other 2. So we're swapping back and forth between those pairs of information. Okay, that was a really long problem. Guess what? There's more. .2. You ready? This question asks, it says the 2 forces that are in pounds, and then it gives us 2 vectors, are applied to an object. Find the equilibrant of the forces. Now last time they told us to find the resultant, and I wrote down that resultant means the sum, it means add them up. But equilibrant means something different. Equilibrant means the opposing force. So that means we're going to have to do a little bit of extra work in finding our answer because it's not going to be just the resultant. And let me go back. Here it is. Make sure you look for these words because they can hide clever little tricks. Okay, so we'll worry about that at the end. Let's just go ahead with our problem. Ready? Our two vectors are 4 at 50 degrees and minus 6 at 170 degrees. All right, we'll have to be careful with that. But this 4 is nice and simple. 50-degree angle. We know our hypotenuse is 4. We know how to do this quickly, right? 4 times cosine of 50 degrees, 4 times sine of 50 degrees. This will give us the right side. This will give us the upside. Beautiful. We run that through the calculator and we get 2.57 and 3.06. Take time right now to grab your calculator and do those calculations. Make sure you get the same as me. If you don't, message me right now. Okay, then we'll do the same for this, but this is tricky. And I'm going to draw the full grid for this one. This says go 170 degrees. Okay, 2 of these would be 180, so I know it's going to be like this, and this would be 10 degrees. But we're supposed to go in the opposite direction, so that means our triangle's actually down here. This is 10 degrees, and this is 6, right? Because this means throw it in reverse, and instead of going in the regular direction, 10 degrees, go backwards 10 degrees. Or 6 units, I'm sorry, 6 units. And we know it's 10 degrees because this is a vertical angle, right? Okay, so this is the triangle we actually want. The right value is 6 times the cosine of 10 degrees, and this is 6 times the sine of 10 degrees. This is 5.91, and this is minus 1.04. Remember that the trig functions have signs, right? They're on your unit circle. You can look at that to reference them. But we also drew a little diagram last year. Remember this? This tells us the value of the trig signs in the different quadrants, sine, cosine, tangent. So we can always double check. So here we are in the 4th quadrant. So that means that sine should be negative and cosine should be positive. That makes sense. In the 1st quadrant, everything's positive, so that makes sense too. So remember to check your minus signs. Ooh, that is a tricky spot for me. I often forget to check my signs of my functions, so be careful with that. All right, now we're ready to add them together, right? We're gonna go sine number right, sine number up. That's the first triangle. Here's the second triangle. And then we shall add them and get a resultant. Okay, plus 2.57 plus 3.06. So that's the first triangle. Then it's plus 5.91 minus 1.04. So our resultant, if you will, is plus 8.48 to the right, and this will be plus 2.02 to the up. Okay, that's really good. This is our new angle, our resultant angle. But John doesn't want the resultant, he wants the equilibrant. Okay, so that means we have to take it back into polars. We can't find the equilibrant in rectangular. So no, we know for sure we have to take it back into polars. I'm gonna switch pages. I'm gonna recopy our rectangular up here. It was plus 8.48 to the right plus 2.02 to the up. Okay, so that's looking like first quadrant. I like that. I try to make it proportional, but I'm not worried about being exact. So it's gonna go kind of like this, right? Because this is the longer side. This is gonna be 8.48, and this is gonna be 2.02. I need to find this angle, which I call theta, and I need to find the hypotenuse because I want, first I'm gonna find the resultant. I'm gonna find that and I'm gonna write it in a box like this. That's my next step, right? Okay, so how do I do that? Well, this I use Pythagorean. So h equals the square root of 8.48 squared plus, and I'm gonna put this in parentheses just to remember, just to remind you that that's what you need for your calculator, right? You can use your calculator to do this. 8.48 squared plus that squared, add them up, find the square root, and you should get a hypotenuse equal to 8.72. And again, this is the resultant, so I'll write it up here, 8.72. And now we need to find the theta. So we know that the tangent of theta equals opposite over adjacent. We use the inverse function key again because we know we can make this into a decimal number. Then we use tangent 1 to tell us what the degrees are. And we get theta equals 13.40. So that we can put up here too. We don't have to adjust that this time because this angle is just exactly what we want for our answer, okay? But we want the opposing force, right? We want the equilibrant. So the nice thing is it's really easy. The opposing force would be in the opposite direction . Same distance. And the easiest way to write that is to simply put a minus in front of the hypotenuse. Because what that's saying is, go measure this, which is the 13.4 degrees, right? That's our theta. And then go 8.72, but don't go in the positive direction, go in the opposite direction. That would be negative h, right? So that's how we can find the equilibrium, is just take the opposite of that number. And this, finally, at long last, is our answer. Whew. Okay, there's one more of these. And then we have our second topic. Oh my gosh, John is a taskmaster. Example 30.3. I hope this is all coming back though. All right, what vector force must be added to a force of 20 at 30 degrees newtons to obtain a resultant of 25 0-degree newtons? What in the world? Okay, so what John's saying is, here's one angle. and we're going to add another angle, and the answer is going to be this, right? Because he says the resultant, and I'll tell you again, that means the sum. Okay, so he's playing a fancier game with us this time. He's giving us one of the angles and he's giving us the total, and he wants us to find the other angle. All right, we can do that, right? First, we want to convert everything to rectangulars, and this time we'll actually subtract, right? But I'm getting ahead of myself. First, let's do this one, 30 degrees. Okay, that's a first quadrant angle. This is 30. This is 20. No, that doesn't get the degrees. That does. So we do the right will be equal to 20 times the cosine of 30 degrees, and the up will be equal to 20 times the sine of 30 degrees. Grab your calculator, run the numbers through. Here's what I get. Okay? Yay! So far, so good. Now, we don't know the other angle, but we want to convert the answer into rectangular coordinates as well. This number is at 0 degrees, so I'm not actually going to be able to draw 0 degrees, but I'm going to make it close. This tells me that I can find this. I don't even need trig functions, because I can see this point is just on the regular spectrum. This is going to be 25 and this is going to be 0. So it is, my right value is going to be 25 and my up value is going to be 0. That's so easy it's hard, right? That point literally lies just on the grid. There's nothing fancy about it. We can see it super easily. Okay, so this angle, 7.32 right plus 10.00 up plus some other number has to equal that. Does that make sense? If we call this triangle A and this triangle B, then we know that A plus something else has to equal B. See how I've put those into this? So now all we have to do is a little bit of subtraction. 25 minus 17.32 backs us into an answer of plus 7 point, let's see what it would be, 68 to the right. Right now it adds, I'm just using subtraction, 25 minus that to get me that. And then 0 minus 10 gets me minus 10, I'll put the decimals in, to the up. Now this adds, and so this is the triangle, I'll call it C. That's our mystery triangle, right? Yay! Now, the only problem is John asked us to find the resultant. That means polar coordinates. So we have to convert this guy into polar coordinates. Are you ready? I'm going to copy him over. It was plus 7.68 to the r's minus 10 to the ups. All right, so what quadrant would that be? That's going to be fourth quadrant, isn't it? Because the right value is positive, but the up value is down. I'm going to put it about here, because this looks like 7.68 and this is 10. Okay, we want to put it into the shape of this, whoops, right? This is how our answer needs to look. We know we use Pythagorean to find this. So it will be h equals the square root of 7.68 squared plus, and then you use parentheses in the calculator for the second part. Oh, 10 squared. You can probably do that in your head. 100, right? So when you simplify that with your calculator, you'll get h equals 12.61. Yay, that goes here. Okay. And now we're trying to find this angle, but remember we'll have to measure it. We'll have to adjust it that way, but we'll call this theta. We'll say the tangent of theta equals opposite ten over adjacent 7.68. You'll generate this as a decimal number, and then you'll use the inverse tangent key, and you'll get that theta equals 52.48 degrees. Now, here's a fun little cheat. We could take the whole total of 360, like I said. Oh, I need to go all the way to there. We could take 360 and we could subtract this 52.48 to get this whole measure. Or we can take a shortcut and we can just say, oh, let's just measure in the opposite direction, 52.48 degrees, and that will give us exactly what we need. Tricky, right? So this is a lovely answer. All we want to do is just put a unit on it. I don't really understand how that unit affects anything. I don't really have a grasp of the science of that, but it's okay. I don't need to. I just know, oh, John said that it says what vector force must be added to blah, blah, blah newtons in order to get a resultant of blah, blah, blah newtons. So this must be newtons too, and I can just say blah, blah, blah newtons. Yay. Don't let the words freak you out. All right. Now, as if that wasn't enough, John has a couple quick proofs he'd like us to bomb through. So, shall we? I mean, right? Not like that stressed you out or made you tired or anything. Overlapping triangles. Here are a few classic pictures that John's going to get us used to. And we're just going to do proof outlines. I do not care about the formality of how you write this out. Here's our picture. It looks to me like the kind of hat that like the dudes at In-N-Out wear. They're those paper folded hats. Okay, pretend it's perfect. It's not terrible, but A, B, C, D. So we can see that these two triangles can be pulled apart. So I'm going to write them separately. Pretend those are perfect, which they're not. This one is A, C, D, and this one is A, B, D. Okay? Now, the given information is that segment AB is congruent to DC. Okay? So that'll be our step one in our statement and reason chart. Statement, reason. And now we'll put that on our pictures. We'll put it on these. AB is congruent to DC. Okay, good. There's a matching side. And then so that's given. And then the second thing we're given is that segment BD is congruent to CA. Okay, let's figure that one out. BD is congruent to CA. Okay, that's good. I like it. Now, that's also given. That's two sides. What could we say about the third side? Maybe we can find a way to show that they're the same. And when we look at it, we go, dude, it's the very same thing. It's AD, right? Because this segment is in both of the triangles. So we can say segment AD is congruent to segment AD. And remember the ridiculous name we give when things are just already the same is we call them reflexive. Because it's like they're looking in the mirror at each other. Oh, it's, yeah. Reflexive, reflective, close enough. Now we have proved, oh, what we're trying to prove, sorry, I didn't tell us that. We're trying to prove that triangle ABD is congruent to triangle DCA. So ABD, DCA, we're trying to prove that these two guys are the same. We see that we've got two sides of the same. We could do side angle side, but I don't have anything on B and C. But I see that this side is the same, so when we go for, oh, I already said all this. We go for that, and then we get triangle ABC is congruent to triangle DCA, and we proved that, whoops, for by side, side, side congruency postulate. Hot diggity. We did it. That's right. That wasn't that bad, right? And we have two more little, two more to go. Hope my light holds. It's getting dark in here. Example. It would be a shame if I ran out of light and I had to start filming, wouldn't it? Gosh, that'd be a big bummer. All right, this picture looks like this. Again, pretend it's perfect. We'll put letters on it. P, Q, R, X, Y. We'll start our list. Oh, let's pull the triangles separate from each other. So it'll be like this with P, Q, Y, and then it'll be like this with R, Q, X. So one of the things I want you to take away from these problems is that when you see these certain shapes, you automatically pull them apart into two triangles. If we can reduce a shape to triangles, we then can prove congruency of the triangles and go from there. But we don't have any congruency postulates for a shape like that. We have to make it into triangles. Okay, statement and reason. And let's start with what we've been given. 1, PQ is congruent to RQ. Okay, PQ is congruent to RQ. Okay, I like it, that's given. 2, Q Y is congruent to QX. Oh, okay. QY is congruent to QX, and that's segments. So QY is congruent to QX. Okay. That's also given. And what we're being asked to prove is that triangle PQY is congruent to RQX. PQY, RQX. Okay, we're trying to prove these two guys are congruent. We've got two sides established, so we have to look and see what else we've got going on that we could use to get either, we've got side and side so far, right? So we could get side, angle, side, or we could get side, side, side. So let's look at side, 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 because that's what we used last time. But this time our third side, it doesn't have anything to do with each other, right? This is PY and this one is RX. There's nothing we know about them that overlaps. So that makes me sad. I don't think side, side, side is gonna work. But let's look at side, angle, side. Side, angle, side. Q is the angle in between them. Oh, but look. And this one, right between the two sides, Q is also the same angle. So we can mark that the same, and we can write, once again, angle Q is congruent to angle Q because reflexive, it's the same frickin' thing. And so now we're good. We can say triangle PQY, I'll just use John's order of the letters, is congruent to triangle RQX. And this time it's by reason of side, angle, side, whoops, side, angle, side. I was already thinking about the next part. Congruency postulate. I like to write that because it makes me feel smart. Done. We did it. Right? So the takeaway is these shapes are very distinctive. This side is always going to be the same. And you can notice that as soon as this paper hat thing comes up. This one, I'll tell you what, it reminds me a little bit of the communicators on Star Trek, you know, the little devices they wear on their shirts and they tap when they want to talk to each other. It's sort of like this. And here, pay attention to the fact that this angle is going to be the same when we pull the two triangles apart. All right? So these are the patterns that geometry people love to play on. And then there's just one more. Wait. Yeah, there is. I thought for a second there wasn't, but there is. Okay, ready? Example 30.6. Here it goes. It looks like this. It's an actual triangle, but then it's got smaller ones built inside of it. Okay, X, Y, Z, and UV. No W, sorry. Okay, let's pull, oh wow, when we go to pull this apart, there's a lot, okay? First thing we're gonna do is we're gonna pull apart, here, let me just write it. ZXV. And this one is ZUY. This is kind of confusing. I'll write it on the inside for both of them. Okay, ZXV, ZXV, ZUY, ZUY. But we can also do these little triangles down here. And they would be XUY, I'm writing that on the inside because I wrote these so close together, and VYX. All right, so we have 4 triangles that come from this shape. Again, these are classic shapes that proof buffs will use again and again. So as soon as you see them, And we'll learn in just a minute what they are. There are certain truths about them. Okay, given segment XZ equals segment YZ, or is congruent to. And that's given, let's add it. X, Z is congruent to YZ. Now that doesn't show up on our smaller triangles. It only shows up on the bigger ones because the bottom ones are just down here, right? Okay. 2. XV is perpendicular to YZ. Okay, XV is perpendicular to YZ. Let me make sure I wrote that right. XV, YZ, perpendicular. So let's take a look at that. XV is perpendicular to YZ. Okay, so this comes in at a right angle, is what they're saying. So that means this is a right angle, and this is a right angle, right? 2 given. 3, YU is perpendicular to XZ. YU is perpendicular to XZ. Okay, let's figure that one out. YU is perpendicular to XZ. So this is also a right angle. So that means angle U is a right angle and angle U is a right angle. Okay, so we've got information about angles there. Write a 2-column proof to prove that segment XV is congruent to YU. XV is congruent to YU. So what does that look like? XV is congruent to YU. So that's what we're trying to prove, that those two are the same. We could do that with either triangle, couldn't we? Because here's XV and YU, and here also is YU and XV. So either set of triangles could work for us. Now, what else do we know? Just like we did last time, we pay attention to this angle at the top because angle Z is in multiple of these angles, isn't it? It's right here, and it's right here. All right, that's interesting. This was also given. I didn't write that down. So, I didn't write this as completely as I could. I could have written more about how that means angle U is a right angle and angle V is a right angle, but that's kind of implicit, right? That those are right angles. I can also say, oh, I said this already, angle Z equals angle Z, or is congruent to. That's reflexive. And look what I've got now. I've got angle, angle, side, right? I proved it with these right angles, where we were told that they were perpendicular. That tells me those two angles are the same. So now I can say that triangle X, Z, V is congruent to triangle YZU, and I can do that by angle, angle, side, right? Angle, angle, side. I don't really need these two triangles in this example, but I wanted you to see how we can pull them apart and gather information on them as well. I need these two because I want to take advantage of this truth up here. Angle, angle, side, and then we can also write this if we want, because if you have two angles, then you have three. Some teachers prefer one over the other. I like to write them both. Congruency postulate. We'll just write post. And then our final step is to say that segment XV, which is here, is congruent to YU, which is here, YU, because, do you know why? Because corresponding parts of congruent triangles are also congruent. Woohoo, we did it. Proven. 3 more shapes that are fun to use for proofs because we can pull them apart and get triangles, and that's our objective in proofs, is to reduce these more complicated shapes to triangles and then use the different postulates we know for congruency, right? Side, 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 angle, side, hypotenuse, leg. Those are the 4 postulates of congruency. We use those to prove that the triangles match. I'm done. I'm speechless, honestly, after all of that. Thank you. Good luck. Goodbye.